Okay, what we're going to do today is design a steam power plant. Now, steam power plants are close to my heart because if I hadn't gone into computers, I would have gone to work at Madison Gas and Electric in their coal steam power plant. Now, in the United States, coal steam power plants are used in coal. 50% electricity comes from coal, natural gas, 20%, and nuclear. Nuclear is a heat generating process, and we use this splitting of atoms to generate heat, and therefore 80% of the power, electrical power in the United States is going through a steam power plant. Okay, so let's go and remember our ideal gas law. Pressure times volume is equal a constant times temperature. And what we're going to do in this steam power plant is we are going to crank the temperature up, just like we did in the exploding paint can, and accordingly pressure is going to go up like crazy. So let's start. We have a boiler and we put water in it. This is our boiler, and we put heat, flame underneath it. Heat. Now, if we don't do something, this will explode. Well, the difference between a boiler and exploding paint can is we take the hot 1,000-degree steam. The water is at 700 degrees because it's under pressure, and water doesn't boil at 212 if there's pressure on it. It can go up as high as 700 degrees. We try to take this as high as the metal can go. Now here's a very nice breakthrough that physicists made called the steam turbine. And it's kind of like a jet engine. It has vanes, back and forth vanes, like a jet engine. And our steam is sent through this steam turbine actually in 3 stages: high pressure, medium pressure, and low pressure. So every drop of pressure and power that's in this steam is turned into this, uses energy or power in this steam turbine. Now this steam turbine has a shaft, it's rotating, it has a shaft, and it is connected to a generator. And our generator is 2 magnetic fields rotating next to each other. And electrical engineers call this electricity and magnetism. And when you have 2 magnetic fields rotating next to each other, you get electricity. Out pops electricity. So, and a generator is basically a motor backwards. Now, what's happening here is that this steam turbine is turning at 3,600 RPM, and it's applying a torque to this shaft, and that torque at 3,600 RPM is turning those magnets and generating the electricity. Now, another equation of power is horsepower is equal to torque times RPM. Now, in the mechanical world, we also had the definition of horsepower, where we had the horse lifting 550 pounds 1 foot every second. So that was linear translation. Now, in rotation, we use a different equation, which is torque, which is force times distance. It's the desire to twist something, and it's times RPM. So we have 3,600 RPM here. To drive the 60 hertz electricity that is in US Power. Okay, now after the steam has gone through the 3 pressure drops, we bring it out and we take it into a heat exchanger, or a condenser. Okay, so this condenser has cooling water cycling through it. So there's a pump down here running cooling water from a lake, river, or ocean through this condenser. So you're taking this hot steam over here and you're turning it back into water. You've got to get it back into water we have a pump here that's taking that water and putting it back into the bottom of our boiler. And the magic here, the important thing here is to know that steam power plants are a closed loop system. This steam and water in the system never leaves it. The water from the lake or something is run through a set of veins here, but that somewhat dirty water, maybe having algae in it, never touches the steam that's in the system. So we want to keep this a nice closed loop system. That is why we need the cooling water, because to get massive power, we need massive temperature differences. So if you've got steam at 1,000 degrees up here and you've got it back into water here, you can get an amazing amount of energy, because we know that PV is equal to nRT, and the bigger that temperature difference, the more that pressure changes. Now, one thing that's interesting here is that if you take a coal power plant, this power plant is burning 100 train cars of coal a day. 100 train cars of coal one power plant is generating. In the summer, when the refrigerator or air conditioners are on, you get 300 train cars a day. So this is a massive amount of CO2 that's going into the atmosphere. Every single day, 100 to 300 train cars are being burnt by every one of the coal power plants. Coal power plants are about 1 gigawatt, and we need 10,000 of these. So it is a considerable amount of coal being consumed by coal power plants. So this is the way that electricity is generated, and I'm telling you this because I want all of the energy experts to know how much is going in, how much power is coming out, the equations that are being used to determine the torque and the horsepower to this generator, and just have an understanding of where electricity comes from, and has a concept that we can dig deeper into the energy distribution of coal, natural gas, and uranium in the United States. So once again, we can be experts, energy consultants in the future when we graduate from college. That's it.